Okay. So we have introduced the Maxwell equations and boundary condition about these four equations when we consider waves reflecting or reflection by some interface. Now we consider the energy issue. We now try to derive some consequence about Maxwell equation, which is related to the electromagnetic energy density . Before I derive this consequence, I want to show you that we can derive some energy conservation law from Newton's law. Okay. For example, we consider Newton's law. Okay. Newton's law applied to harmonic oscillator. Okay. Consider this . Consider this problem. We consider a mass block connecting to a spring. The spring constant is K. So we want to consider the oscillation. According to Newton's law, F is equal to minus K x is the displacement from the equilibrium position 从平衡的位置呢的位移这边有一个负号this minus sign means that the spring provide a restoring force 一个回复力。So this restoring force provide the acceleration. This is Hooke's law, and this is Newton's law, second law. Okay, we combine these two laws, we get mx double dot plus kx equal to 0. Okay, here x double dot means the acceleration. So if we remember that velocity is x dot， 就是说，位移的一次时间微分呢是速度，两次的微分呢是加速度。那现在我们来看一个问题是这样，我们从微积分里面according to calculus, if I times this equation, this is equation of motion. Now I times x dot multiply x dot to this equation. We get 0. However, x dot times x double dot means x dot times dt dx dot if you treat x dot as a variable, this means dt d 1/2 x dot squared. Okay. Now, x dot times x is similar to this, but this time we have this. So this is equal to dt d 1/2 x squared. Okay. So with this multiplication combined with the knowledge of calculus, we now can obtain this. This means that this quantity is constant of motion. Which means that although we see that the oscillator oscillated back and forth, but in this process, this quantity is always keep unchanged. 就这个东西永远不随时间改变。那大家其实学过力学，知道这是什么东西？这是动能，这是位能啊。This part is kinetic energy, and this part is potential energy. You can apply the similar consideration to, 比如说 two-dimensional, three-dimensional mechanics problem and get something like this. You will find mechanical energy conservation. Now we apply the similar concept to these two equations. These two. You have learned in electrodynamics that electric field energy density in material can be written as UE is equal to 1/2 E dot D. And the magnetic field energy density UB is 1/2 H dot B. So if we assume that D is proportional to E and B is proportional to H, the total electromagnetic energy density can be written as U equal to UE plus UB, and this is 1/2 H E dot D plus H dot B Now we differentiate it and use these two equations. Now I want to know how the total EM energy density vary with time. I differentiate this quantity 1/2 partial T partial